We now start the third module of chapter 5 and we will be talking on the projection operators. We will understand the notion of projection of a vector on a given subspace. We will also introduce what is called orthogonal projection, and we will see that it is somewhat different from the usual notion of projection. And finally, we will learn the least square approximation, which is extremely important and useful. Let V be an inner product space over the field F, which is the field of real or complex numbers. Let W1 and W2 be subspaces of V such that V is the direct sum of W1 and W2. Therefore, by the definition of direct sum, every vector V in V can be written uniquely as W1 plus W2 such that this vector W1 is coming from the subspace W1 and the vector W2 is in the subspace W2. We now define the projection operator as a linear operator T on V, and it is called a projection on W1 along W2 if given V is equal to W1 plus W2, we define T of V is equal to W1. We often call such operators by just projection and we hide W1 and W2 when it is clearly understood. Now, a very important property of a projection operator. The proposition says a linear operator T on V is a projection if and only if T square is equal to T. Proof. If T is a projection, then it is clear from the definition that T square is equal to T. Why is that so? Because we start with a vector V, decompose it as W1 plus W2, and then T of V by definition is W1. And we know that this decomposition is unique, and therefore when we apply T again, then it is nothing but T of V, which is W1. Conversely, given a vector V, we write it as V is equal to TV plus V minus TV, and it follows that V is the direct sum of these two subspaces, namely the set containing W such that T of W is equal to W and kernel of T. Therefore, T is a projection on the subspace set of all W such that TW is equal to W and along the subspace kernel of T. Now, a remark, if T is the projection on W1 along W2, then range of T is equal to W1 and kernel of T is equal to W2, and V is W1 direct sum W2, that is range of T direct sum kernel of T. However, it can happen that W1 direct sum W2 is the same as W1 direct sum W2 dash, but W2 is not the same as W2 dash. Therefore, given W1, the projection T is not uniquely determined unless W2 is explicit. We will see that in the case of an orthogonal projection, this is not the case. Let us now define the orthogonal projection. So, a projection operator T on V is called an orthogonal projection if range of T perp is kernel of T and kernel of T perp is range of T. You know what perp means, that means the orthogonal complement. Another remark, if the inner product space is finite dimensional, then it is easy to prove that given X outside W, there exists Y in W perp such that the inner product of X and Y is not 0. And this can be used to show that W perp is W. Therefore, range of T perp is kernel of T and kernel of T perp is equal to range of T are in fact equivalent. So, just one condition would be enough for an operator which is a projection operator to be an orthogonal projection. Now, the following proposition shows that an orthogonal projection is uniquely determined by its range. Before we start with the proposition, let us look at the diagram which shows the difference between a projection and an orthogonal projection. So, in the picture, W is the subspace spanned by the vector 1 1 in R2, which is the line passing through 0 0 and 1 1, and given V in R2, the PV point denotes the foot of the perpendicular drop from V on the line W, and therefore P is the orthogonal projection, whereas the point QV that you see on W is coming from another projection Q. Now, they are indeed different, which can be seen from the fact that V minus PV is actually in W perp, but V minus QV is not in W perp. Now, the proposition. So, let W be a finite dimensional subspace of the inner product space V over F. Then there is a unique orthogonal projection of V on W. Proof. Let V belong to the vector space V. Then we know that V is equal to X plus Y for unique X in W and Y in W perp. Define T V is equal to X, which is an orthogonal projection on W. Now, let T dash be another orthogonal projection on W, that is range of T dash is equal to W, which is the same as range of T. Therefore, kernel of T, which is range of T perp, which is the same as range of T dash perp, and that is kernel of T dash, and therefore T is equal to T dash. Now, a remark, let B the set of the vectors V1, V2 and so on up to Vk, Vk plus 1 and so on up to Vn be an orthonormal basis for the vector space V, such that the set of the first k vectors, that is V1 and so on up to Vk, is an orthonormal basis for W. Then the matrix representation for the orthogonal projection operator T on V is given by this matrix in the block form, where the top left corner is the identity matrix of size D and O1, O2, O3 are suitable 0 matrices. And what is this D? D is nothing but the dimension of W. We have learned definitions of projection and orthogonal projection operators, and now we will learn some equivalent criteria for orthogonal projection, and that would involve the adjoint operator. We will see that this concept of orthogonal projection will play an important role when we talk about the spectral decomposition. Theorem: let V be an inner product space over F and T a linear operator on V. Then T is an orthogonal projection if and only if T star exists and T square is equal to T is equal to T star. Proof: suppose that T is an orthogonal projection, then T square is equal to T, and we have to prove that T star exists and T star is equal to T. We know that V is the direct sum of range of T and kernel of T, and range of T perp is kernel of T. Let V and W be two vectors, then we can write them as V is equal to V1 plus V2 and W is equal to W1 plus W2, such that V1 and W1 are in range of T and V2, W2 are in kernel of T. This gives us that the inner product of V with TW, that is inner product V1 plus V2 comma W1, that is equal to inner product V1 comma W1 plus inner product V2 comma W2, and that is equal to inner product V1 comma W1. And similarly, the inner product TV comma W is inner product V1 comma W1 plus W2, and that is inner product V1 comma W1 plus inner product V1 comma W2, and we finally end up with inner product V1 comma W1. Therefore, we see that the right hand sides match and therefore the left hand sides match. Therefore, inner product V comma TW is the same as inner product TV comma W. Therefore, we conclude that T star exists and it is nothing but T. Conversely, let T square be is equal to T is equal to T star, then T is a projection, because we have already seen before that T is a projection if and only if T square is equal to T. The only thing we have to show now is that it is an orthogonal projection. So, let us start with a vector V in range of T and a vector W in kernel of T. Then V is equal to T of V is equal to T star V, and therefore, the inner product of V and W is inner product T star V comma W, that is inner product V comma TW, and that is inner product V comma the 0 vector, therefore, it is 0. This therefore shows that the vector V belongs to kernel T perp, and hence range of T is contained in kernel T perp. Let us now start with a vector W in kernel T perp, and we show that T of W is equal to W, and therefore, W will be in range of T. Now, we have that norm of W minus TW square is inner product W minus TW comma W minus TW. This is therefore inner product W comma W minus TW minus inner product TW comma W minus TW. Hence, inner product W comma W minus TW is 0, since W minus TW belongs to kernel of T, and also inner product TW comma W minus TW is equal to inner product W comma T star of W minus TW. We are using the adjoint here, and that is equal to inner product W comma T of w minus tw, that is because t star is equal to t, which is given to us, and that is the same as inner product w comma the 0 vector, and therefore it is 0. Hence, we have proved that range of t is equal to kernel t perp. Now, if V is finite dimensional, then we are done, because automatically then range of t perp would be equal to kernel of t. If not, then we also have to show that range of t perp is equal to kernel of t. Now, we have range of t perp is kernel of t double perp, which contains kernel of t. Let us start with a vector v in range of t perp. Then given w in v, we have inner product tv comma w is equal to inner product v comma t star w is equal to inner product v comma tw, and that is 0. Therefore, tv is 0, that is v belongs to kernel of t. Least squares approximation. Let t1 x1, t2 x2 and so on tn xn be n points in the real plane R2. Here we assume that the base field is the field of real numbers. Suppose that we want to determine a line x is equal to a plus bt such that a and b are real numbers, and that the sum of the squares of the vertical distances of the points t1 x1 comma t2 x2 and so on tn xn from the line is minimum. That is, this quantity E, which is summation I equal to 1 to n xi minus bti minus a square, is minimum. And the problem is to find constants a, b such that E is minimized. And the line x equal to a plus bt is called the least squares line. If we rewrite this problem in matrix notation, then this matrix A, which is an n cross 2 matrix given by the first row T1 1, second row T2 1 and so on, the nth row Tn 1, and then V is this column matrix BA, and X is this column matrix x1, x2 and so on xn. Then E is nothing but norm of x minus AV square, and the problem can be generalized in the following form. Given A, an m cross n matrix over R, we want to find V0 in Rn such that norm of x minus AV0 is less than or equal to norm of x minus AV for all vectors V in Rn. Now, this lemma will be useful for proving existence of that V0. Let A be this m cross n matrix, then inner product Ax comma y is the same as inner product x comma A star y for every x and y, where x is in Rn and y is in Rm. And the second part says that rank of A star is the same as rank of A. Proof of part 1, inner product Axy is the same as y star Ax, that is by the definition of the usual inner product, and that is y star Ax, that is A star y whole star x, and that is inner product x comma A star y. And part 2, by the rank nullity theorem, it is enough to check that Ax is equal to 0 if and only if A star Ax is 0 for x in Rn. Now, if Ax is 0, then A star Ax is 0. Now, suppose that A star Ax is 0, then this inner product A star Ax comma x is 0, but that is inner product Ax comma A double star x but that is inner product Ax comma Ax. Therefore, Ax is 0. And the corollary is that if A has rank n, then A star A is invertible. We therefore have this theorem, let A be an m cross n matrix and X is a vector in Rm, then there exists V0 in Rn such that A star A of V0 is A star X, and norm of AV0 minus X is less than or equal to norm of AV minus X for all V in Rn. Moreover, if rank of A is n, then V0 is explicitly determined as A star A inverse A star X. Proof: let W be set of all AV with V in Rn, which is nothing but the range of that operator LA, which is the left multiplication operator. Now, we know that there exists a unique vector in W that is closest to X. Let us call this vector AV0 for V0 in Rn, and then norm of AV0 minus X is less than or equal to norm of AV minus X for all V in Rn. This proves the first part of the statement, that is the existence of that V0 such that norm of AV0 minus X is minimized. We have AV0 minus X belonging to W perp, so that inner product AV and AV0 minus X is 0 for all V in Rn. Therefore, inner product V comma A star AV0 minus X is 0 for all V in Rn. Hence, A star of AV0 minus X is 0. Therefore, if rank of A is n, then rank of A star A is also n, and we get that V0 is equal to A star A inverse times A star X. And the remark says that the above proof is constructive in the sense that it explicitly finds the point V0 if A is invertible. We have learnt the orthogonal projection operators, and now it's time to see how they become extremely important when we try to understand decomposition of linear operators on inner product spaces. We will be talking about the spectral decomposition theorem later on, and that is where these orthogonal projection operators will be revisited.